Okay, good morning. Any questions? Yes?
In the half-wave uncontrolled rectifier, we have the form factor of pi by 2. So similarly for the controlled half-wave rectifier, is there a value, it depends on alpha and beta, right?
Right.
So is there a range of values for, alpha is near pi by 2, so?
Alpha and beta, when you have an RC load, you mean? Or
For RL load.
for an RL load. Is there a range for that?
Yeah.
Well, so I guess let me repeat the question. The question is, do we have a range for alpha and beta when it comes to a full wave rectifier when the load is an RL load? Is that the question?
Yeah.
Okay. Well, alpha is up to us. We can determine alpha whatever value we want to choose. So alpha is our basically control input. We can choose it whatever we want it to be. Beta is determined by what value of alpha we have chosen and what the value of the inductor is. So actually the circuit determines what the value of beta is. Now, beta comes into the picture as long as your current is discontinuous. If your current is continuous, you don't even have a beta. Before the beta arrives, your new alpha arrives. So you have to trigger the devices on again. So the general answer would be no. We don't have a specific range. We can choose whatever we want. And then depending on the parameters, beta is determined by that, assuming that we are in a discontinuous mode of operation. I mean, alpha could be any number, like 10 degrees, 20 degrees, 30 degrees, 40 degrees, whatever you want it to be. There's no specific range. Other questions? Okay. So what we did last time was we kind of wrapped up chapter 4. The main topic of discussion was three-phase rectifiers, like the schematic that we have over here. We have a three-phase Y-connected source balanced, and then we use 6 diodes in 3 legs to kind of rectify this voltage and provide some DC power to the load. As it turns out, even without using an inductor to smooth the current or a capacitor to smooth the voltage, even just with a purely resistive load, our output voltage is relatively DC. It's actually in a good shape. As it turns out, we have to figure out which diodes conduct, and the order of these diodes, the way they have been numbered, are important. First, D1 and D2 conduct, then D2 and D3 conduct, and D3 and D4 conduct, and so on and so forth. It's actually like a loop. And depending on what diodes conduct, you are going to realize, for instance, on the positive terminal of the output voltage, you are applying VAN, which is line to neutral voltage of the line of the source. And if, for instance, one of the bottom diodes, whenever it is conducting, for instance, let's say VBN is conducting, if VBN is applied to the negative terminal. So when you want to try finding out the waveform for the output voltage, you have to look at all of the line-to-line voltages like VAB, VAC, VBA, VBC, VCA, and VCN. And these are actually all drawn over here. So this AB means that this waveform over here is VAB. And for 1/6 of the period, this is actually the voltage that is determining our output voltage. And then diodes, for instance, 1 and 2 conduct, and then VAC is our output voltage. Then diodes 2 and 3 conduct, and then VBC is our output voltage. So this is what we discussed last time. Then I very briefly talked about what if we have a controlled rectifier. We did not get into the details of this. Similar to before, the controlled rectifier is actually introducing some sort of a control variable for the user to, for instance, adjust the DC or average value of the output voltage. For instance, the application could be you have a power supply and you want to basically adjust the value of your output voltage. Or you have a, for instance, DC motor, you want to control the speed of this DC motor. And the speed is determined by how much voltage you're applying to the terminals of your motor. So using, having those applications in mind, then you can use SCRs instead of diodes. And then, for instance, if D1, if this was a diode, it, for instance, would have started the conduction over here, right at this point. But because it's an SCR, it waits for your command. If you trigger it at the right time, and for instance your command is delayed by an angle of alpha, now it's actually triggered over here, and this is the SCR that is conducting until the next SCR is triggered, and then you kind of having an output voltage like this, which is actually lower than the case if you only had diodes. So remember that the highest DC voltage that you want to achieve is achieved using diodes, or if you have SCRs, it is achieved by using alpha, which is the triggering angle, to be 0. But then if you need lower than those, you can actually achieve those. I'm going to briefly talk about chapter 5. It's a relatively short chapter, and they are called AC voltage controllers. They don't really, these kind of converters do not really fall under the classic way of categorizing converters into DC to DC converters, or AC to DC rectifiers, or DC to AC inverters, or even AC to AC converters, because as it turns out, you don't really change the frequency of the output with respect to the input, or you don't really change the amplitude of the output with respect to the input. All you do is you all have an application that you want to control the power, the amount of power that is delivered to your load, and your load is a resistive load that is supposed to generate heat or light. For instance, a conventional light bulb, or an electric oven, or I don't know, an electric water heater, things like that. And well, first, in this chapter, what we are going to talk about is mostly the single-phase applications. Obviously, the same thing applies to three-phase applications. So, if you remember when we were discussing the half-wave rectifiers, the control version, we were looking at a circuit like this. So imagine that SCR number 2 does not exist, and all of a sudden you are reduced down to the conventional controlled half-wave rectifier. As it turns out, with this configuration, you can kind of harvest power from your source whenever the value of the input voltage is positive. So technically, you have the option of, let's say, assuming that this is my input voltage. Whenever the input voltage is positive, you can basically get some energy and apply some voltage across your load. And whenever the input voltage is negative, nothing is happening, because even if you trigger the SCR, because the SCR is reverse biased, nothing really happens. There is no, power going. So the idea is, okay, if this thing can, using only SCR number 1, we can actually have some sort of a control over here. What if I put another SCR over here, kind of in parallel with that, and in a kind of a flipped kind of a thing, and use SCR number 2 to deliver power when the input voltage is basically negative. So this is the very basic, simple idea. So the way it works is, let me clean this a little bit. So let's say this is my, I don't know why it doesn't clean that. Hold on. Okay, it only makes sense to trigger SCR number 1 when the input voltage is positive, so we're actually triggering it over here. And then for the other one, oops. Oh, you're all thick. Okay. And then, for instance, if this is alpha degrees or radians per second, then assuming that we are doing things symmetrically, this is pi plus alpha. So when the input voltage is positive, we trigger SCR number 1. Whenever the input voltage is negative, in the same fashion, we trigger SCR number 2. And for instance, let's say you are interested in plotting the output voltage. Okay. At the beginning, none of the SCRs have been triggered. There's no current flowing through the loop, so everything is 0. And then you trigger the top SCR, and the output voltage falls. So the SCR turns on, and the output voltage and the input voltage are the same. Then we have to see how long this is going to continue, and this is going to continue as long as this SCR is on, and that is as long as this current is positive. At omega t equals to pi, the current tends to get negative, therefore the SCR naturally turns off, and then again nothing is happening here until we trigger the bottom SCR, SCR number 2, and again same mechanism happens. Again, when that SCR is turned on, the input voltage and output voltages are the same, so the output voltage will be negative. So we will be generating some sort of a waveform like this on the output side, which means like we are chopping off part of the input voltage basically. As you can see, the output voltage is not DC anymore, and we don't care because our load is a resistive load and it is just supposed to generate heat, and we just want to control the amount of power or the heat that is generated. So very, very simple. So this is how actually it works. The book has a bunch of equations. Equations are relatively similar to what we have had in the past, and they are also here as well. For instance, first of all, the average value of the output voltage is 0, so there is no point of calculating the average value of the output voltage, but the RMS value may come in handy in case you want to, for instance, calculate the power. So this is the RMS value of the output voltage. All right, so V at RMS is the square root of 1 over pi. You know, by the original definition, you just follow, and you end up having an expression like this. Vm is the peak value of the input voltage. So Vm is basically this value over here. All right. And we have had this case many times before. The output is just a resistor, the output component, so the RMS value of the output current is just the RMS value of the output voltage over the value of that resistor. And then when it comes to power factor, you calculate the average power on the input side or the output side. You look at the RMS value of the input voltage and RMS value of the input current, which turns out to be the same as the RMS value of the output current. And your power factor turns out to be like this, similar to the equations that we have had in the past. Please remember, alpha should be in radians per second when we are using a calculator to find a numerical value. In radians, I'm sorry. All right, the average value of the output current is 0 because it's a symmetric waveform. It has positive areas and negative areas. And then the book goes on and introduces a bunch of other parameters, like for instance, the average value of the current of SCR number 1, the RMS value of the current of SCR number 1, and I mean you can just go on and just define these parameters. They're not that important. And there's an example. It's very, very simple. I will just leave this example to you guys to go ahead and read. And just part C, part of it is actually missing. Let me just rewrite it over here. He's asking about the average value of SCR number 1 current and the RMS value of SCR number 1 current. So we are trying to find these. All right. And in the end, for instance, in this particular numerical example, you can see the power factor is like 72%, not that bad. Then again, make it a little bit complicated. What if instead of just having a purely resistive load, you also have a little bit of an inductance placed in series? And now again, beta comes in. Does beta happen before alpha gets in? You know, the next alpha comes in, or things like that. I'm not going to cover this. Things are pretty much straightforward and easy. You can actually follow that. And I think the book also considers a three-phase case. Let me see. Yeah, again, if you have a three-phase system, let's say you are looking at a three-phase heater, for instance, an all-electric heater, this is actually how you can control the heat that this thing is generating. As it turns out, these are kind of popular topologies, and you don't if you want to implement this system, you don't have to buy two separate SCRs. You can actually buy a one module that includes both SCRs. You know, it has a symbol like this. Like this, which is called a Triac. So it's basically two SCRs kind of back to back in parallel with each other. And then their gates, so this is the gate for both of them, which is okay. You can trigger this gate when the input voltage is positive. This will be only applicable to SCR number 1, and when the input voltage is negative, it's applicable to SCR number 2. But you don't really you don't hurt an SCR if it is reverse bias and you trigger it. Nothing really happens. So this component is out there. It's called Triac, so you can easily buy it. So this is a very basic principle of operation of light dimmers. So if you have a bedroom, you want to adjust the light in the room. When you are basically turning the knob for more light or less light, you are basically changing the value of alpha, something like that. Any questions? All right. So we are going to move on to Chapter 6. Chapter 6 talks about DC to DC converters, which is kind of the main focus of this class, at least from my perspective. The first converter that we are going to analyze is called the buck converter. So we have talked about the applications of these things. For instance, think about your laptop. You know, laptop batteries are around 19.5 or 20 volts. But this voltage is too high for the CPU to consume, so you kind of have to step down the voltage from 20 volts to whatever the CPU needs. For instance, very old times it was 5 volts, then they reduced it to 3.3 volts, then they reduced it to 2 point some volts, and now it's like 1.7 volts. In the future it's going to 1.3 volts or 0.7 volts or 0.9 volts, things like that. So you see that you want to step down the input voltage, which is a DC voltage, to a lower DC voltage, and the buck converter comes in handy. So let's talk about the buck converter. We can kind of categorize DC to DC converters, and we are going to see more of these. So some of the converters just step down the voltage, meaning that the input voltage is larger than the output voltage, like a buck converter, the first converter that we are going to analyze. Some of them step up the voltage, for instance, the boost converter, in which the output voltage is always larger than the input voltage. And some converters can do both, like a buck boost converter, and we are going to analyze all of them. And another way of categorizing converters is are they isolated or non-isolated? By isolation, we mean galvanic isolation. This chapter only covers the converters that are not isolated. Then the next chapter covers the converters that are isolated. You know, there's galvanic isolation in them. There is some sort of a transformer somewhere. So first we talk about the buck converter, which is a non-isolated DC to DC converter, and it's a step-down converter. All right. So let's have a little bit of a deliberation over here. Let's say we have a source. And this source is 20 volts, for instance, the battery of a laptop. And we have a load, for instance, this is our CPU, and this guy needs 5 volts, for instance. I mean, practically CPUs need less than this. And it is, I mean, if you want to model it, it's like a 5 ohm resistance. Again, this is a very inaccurate approximation. I mean, looking at the power that it consumes, for instance, you can say it's 5 ohms. So obviously you cannot directly hook them up to each other, because then the load is going to be happy, the CPU is going to basically burn. The first solution that comes to your mind is, okay, no problem here, I just add another resistor over here. and the value of this resistor should be 15 ohms. So I have a very simple, natural voltage, basically division over here. 5 volts of the input voltage appears across my load, and the remaining 15 volts appears across this resistor that I've added over here. So the solution seems very simple, but there's a major problem associated with this solution, and that is the efficiency. If you look at the efficiency, you're going to realize that the efficiency of this system is only 25%. In other words, you're only delivering 25% of the energy from the source to the load, and the remaining part of the energy is being basically lost over here in this 15 ohm resistor. Okay, so that's not necessarily a good solution. The other problem that may arise is, what if, and that's basically the case, what if this is a variable kind of a load, meaning that at different times it consumes different amounts of power. For instance, sometimes it's 5 ohms, sometimes it's 3 ohms, sometimes it's 2 ohms, something like that. That means you should also have a variable resistance over here as well. Now, building this resistance may become a little bit challenging, but there are solutions for that. So for instance, one simple solution would be just using a transistor over here. All right. By adjusting the amount of current that I'm injecting to the base, I can actually adjust the amount of current that flows through this loop and kind of set the operating point so that even though I have a variable load over here, I always see 5 volts across the terminals of this load, and the remaining 15 volts appears here. All right. So this solution takes care of the fact that what if we have a variable load, we don't really have to stand there and measure the amount of load and then measure the adjusted value of the resistor. It automatically does that. But the efficiency problem still exists, okay? So in worst case scenario, the efficiency of the system is only 25%. So you're generating a lot of heat, especially at a high power kind of an application. These kind of approaches are called linear approaches or linear regulators. So you can actually purchase this unit that would do such a power regulation for you, but they are usually not very efficient. So if you care about efficiency, or if you're processing a lot of power, there's going to be too much heat generated, and then you can't really get rid of that heat unless you have a lot of heat sinks or a lot of fans and things like that. So this is kind of an old approach. So if you buy a very old power supply, like the power supplies that were built back in the maybe 70s or 80s, like a lab power supply, you would see giant switches or basically transistors on the back. You can actually visibly see them from the back, which were sitting on heat sinks, and that's actually what that device is and what it does. So very large heat sinks were required because these systems were not very efficient. All right. So this is not a very power electronics kind of an approach, and let's talk about a power electronics kind of an approach, a power electronic based approach. So remember, we need 5 volts out of 15 volts, to 20 volts of the input. All right. So one idea that may come to your mind is 5 out of 20 is like 25%. What if I only apply my source 25% of the time? Meaning that what if I use a system like this? What comes in the middle is a single pole double through switch. So technically sometimes the switch is in this position and sometimes the switch is in this position, like a light switch, something like that. So you can argue that So if the switch is in the top position or position number 1, the input voltage and the output voltages are the same. If the switch is in the second position or the bottom position or position number 2, the output voltage is 0. So you can argue that what if I do it like this? Keep the switch in position number 1 for 25% of the time, because 5 volts of the output is 25% of the 20 volts. And then keep it in position number 2 for the remaining 75%. Okay? And call this 1 period, and then just repeat yourself. All right, something like this. Okay? So if I do so, if you look at the output voltage waveform, so I'm still working with the 20 volts of input, and this is my output voltage. When my switch in position number 1, the output voltage and the input voltages are the same. So you're looking at 20 volts. And when the switch in position number 2, there is nothing applied, so there is 0. And then 20 volts. And then there is nothing, or 0. And we just do that. All right. So you can argue that this is not the output voltage that you wanted. You wanted a DC voltage that would be 5 volts, but you can see you are generating something that is not necessarily what you needed. But if you look at the average value of the signal, it is actually 5 volts. So if I take the average value of the signal, it will be 5 volts. So all you have to do is introduce an extra stage over there which takes this voltage, which is kind of a square-shaped voltage, and just turn it into, just give us the average value of the signal. Technically we are talking about a low-pass filter. So all you have to do is just introduce a low-pass filter over here. All right. So What do we mean by a low-pass filter? For instance, a second-order low-pass filter looks like this. Just an L and a C. All right. So this L and C are actually, if you design it right, they are like a low-pass filter, and what they do is they take the input voltage, which is kind of this square-shaped kind of a voltage, and then they only deliver you the DC component of this, and then eliminate all the harmonics. And so we have an L, we have a C, this is our load, and this was the 20 volt of the source. So there you go, you have a buck converter. All you have to do is to kind of realize, using the semiconductor devices that we have, realize the switch. Okay? So the way you can realize this switch is using one MOSFET or an IGBT and a diode. So basically this is how it's going to look like. For instance, here I'm using an IGBT. All right, something like this, okay? We don't really discuss why we came up with this idea of this way of actually realizing the switches. This is more like an advanced power electronics kind of a topic, but this would work actually. As it turns out, for instance, we are going to talk about it in details, but when I turn this IGBT on, the diode is reverse biased, so basically I've created a short circuit point from here to here, and when I turn the IGBT off or the MOSFET off, then the diode has to kick in, and the diode is conductor, so there is a short circuit from here to here, the exact same functionality that we need from this very original switch over here. Okay, and you may argue that, okay, some IGBTs have this anti-parallel diode with them, and no problem, this diode over here is never going to get involved. It is as if it doesn't even exist. So that is actually a hint for us. If you want to use a MOSFET, we can actually do so. Instead of this IGBT, you can also use a power MOSFET. And remember, MOSFETs always have this diode with them. All right? So this would do the job as well, depending on what your power rating is, what your switching frequency is. Sometimes it's better to use a MOSFET, power MOSFET, and sometimes it's better to use an IGBT. MOSFETs are usually faster, but they cannot handle a large amount of current. All right. So this is our buck converter. And we are going to spend like today and probably on Thursday kind of analyzing this converter, looking at its different operating points and things like that. First thing that I want to mention is a lot of times they don't draw it like this. They draw it like kind of like this. Basically, let me just read it right down here. And a lot of times you don't really care, is this an IGBT or is this a diode, a MOSFET? You only care that this is just a switch. So instead of drawing a semiconductor symbol, I just draw a switch over here. So this is basically the same. All right, something like this. All right. So I think in the textbook you see this schematic rather than this schematic over here. All right. So before I get to the analysis of this converter, I just wanted to show you a simulation results to prove that it really works, and then come back and kind of analyze the system. Before doing so, I would like to remind you guys, like, have a definition over here about this. Remember, we decided that we needed 5 volts on the output, which is 25% of the 20 volts that we had on the input side. So this gives us a sense about what portion of the time we are in position number 1 and what portion of the time the switch is in position number 2. There is something defined as the duty cycle. So in this particular case, my duty cycle is 25%. So the duty cycle is defined as percentage of time, or maybe time, time that we spend in position number 1 divided by the entire period. Okay, so please remember this is my entire period. Okay, so in this particular example, numerical example that we had, we were spending 25% of the time in position number 1 of one entire period. So for instance, in this case, the duty cycle was 25%, or just 0.25, and there is no unit for the duty cycle. All right? You can kind of redefine this definition, because here we have position number 1 and 2, but down here we just have a switch and a diode. So I'm just going to kind of redefine this definition that we just had. Duty cycle, D, so D is the duty cycle, is defined as on the denominator we have 1 period, and then on the numerator we have the on time of the switch. In each period. All right. Or technically you can argue that this is like T on over 1 entire period. Okay. Because whenever the switch is on, you are as if in position number 1, and whenever the switch is off, you are as if in position number 2. So technically, so if this is the switch command, so the switch command is the command that the controller is applying to the switch, to the gate of the transistor to turn on or off, something like that. So sometimes we are sending an on command, and sometimes we are sending an off command. And then we are doing this periodically. So this would be D times T, okay? And obviously this would be 1 minus D times T. Okay? And then if you add them together, it's the T, which is the period, basically. All right. What's confusing in power electronics, we use a lot of Ds. 1D is the diode. So we usually use capital D for the diode. Okay? Like here we have a capital S for the switch. Then we have this D, the lowercase d, as the duty cycle. And please remember, this D is not differentiation. So basically, when I'm doing, for instance, some sort of an integration, in the end I have like dt. This D is not the diode or the duty cycle. This is the differentiation symbol or whatever it is. So this is totally different. So here I'm not really doing any differentiation. I'm just multiplying my D by T. It's just a multiplication. All right. Then later on, if you take a control class, D is the disturbance that is applied to the system. And a lot of times in our power electronic systems, we also have disturbance as well. So please, differentiate between all of these Ds. So far, this D is just a duty cycle. It's just a number. Has nothing to do with differentiation. All right. So we have this defined as well. Now let's take a look at the simulation that we have. All right, so I have created this simulation file, and I'm going to post it on Blackboard. There is already a box simulation on Blackboard, and that is made in Simulink, which is a kind of a very powerful block, a block set in MATLAB. If you haven't used it before, I highly urge you to do so. For the rest of your life as an electrical engineer, you are going to be dealing with MATLAB and Simulink if they don't go bankrupt. That they are doing well, actually, so they are not. And recently, over the past few years, there is this, I think, German company that has developed this Plex, or Plexim is the name of the company, I believe. And that is, again, a bunch of tools in MATLAB. So technically, if you double-click, I'm going to upload this Plex file on the web. If you double-click, it gives you more like a Simulink environment, and then it's a Plex circuit. And if you double-click on the Plex circuit, it is the Plex components. So if, for instance, you want to add another component, you have to go to like Window, Library Browser, and for instance, we just talked about a Triac. You can add a Triac to your system, something like that. Okay? So all of these components, like this resistor, this cap, this inductor, this diode, this MOSFET, this DC source, they are all there. I mean, let's talk about the DC source, for instance. So they have so this is the category under which all the power semiconductors appear. Then you can look at the sources, and then there's lots of sources. Like I'm using this one. Like, what if you have an AC source, controlled source, current source, voltage source? All of these sources are actually listed here. You can just use them. And then once you select all the components, you just have to kind of do the wiring. So when you put the components, then you have to kind of do the wiring, and they just connect to each other. For this particular this MOSFET that I have over here, I have to turn it on and off. And if you look at the help menu of this MOSFET, basically if you look at help, it determines how it's turned on and off. So technically you need to have a pulse generator, and in this case, for instance, 1 for the MOSFET means it's on, and 0 means the switch is off. And the switching frequency I would like it to be 100 kilohertz, and the duty cycle is 0.6. Okay, so remember, some of these softwares take the duty cycle from you in terms of percentage, and sometimes they are like in per unit kind of a thing. In this particular case, is per unit, so I shouldn't put 60. I should put 0.6, a number between 0 and 1. And do we have an initial phase delay? We don't care, and we don't have it, so let's just go with that. So this guy is actually like our controller that is sending the on and off command to our MOSFET. And in the end, you want to watch a bunch of waveforms so you can actually create a probe. And in this probe, I am looking at the pulse generator output to see the status of my switch, the inductor current, and the capacitor voltage. All right, so let's run it. So you go to simulation and start, and then just double click on this oscilloscope, and you have all the waveforms that you need. As you can observe, initially you have a kind of a transition or a transient, a startup transient. We usually don't care about this, at least as far as this class is concerned. You always analyze the converters in their steady state operation. And as you can see, after a little while, things get settled down and you have reached the steady state, and that crazy transient is over. So our analysis only takes care of that part. So we have to zoom in this area instead of this area. Now you will be surprised, even at like a graduate level class, you assign assignment to the students to run some simulations, and they get different results, final results. And the reason is they haven't run their simulation to reach the steady state. For instance, if you choose the end time of your simulation to be 0.15 times 10 to the power of negative 2, your final result is going to be here, and because you have not reached the steady state, your final result may not reflect the reality of the steady state operation. So please remember, whenever you are simulating a power electronic converter, run it long enough so that a steady state has achieved. Very, very simple. A lot of people forget about that. Now, how do you do that? You go to the simulation parameters, and this tells you, for instance, I'm remote connecting to my office computer. I can grab this down. Okay. Well, obviously the start time is 0. The end time is 10 milliseconds, and I think that's enough for me. And there is lots of other stuff over here that you can actually adjust, make your simulation more faster, more accurate, things like that. But I've already done that. You don't worry about that. Okay. So let's look at some of these results. So I'm just going to zoom in at the steady state part. All right. The green one is the command that we are sending to the switch. So sometimes it's 1, means the switch should turn on, and sometimes it's 0, means the switch should turn off. So technically from here to here, I have 1 period, and I have determined this period to be 10 microseconds because my switching frequency was 100 kilohertz. And as you can see, the on time of the switch with respect to the entire period was it 60% or 70%? Let's go back. 60%. So the duty cycle is 0.6 or 60%. This number over here. All right. And okay, what else do we have? So this was the command that we are applying to the switch. Let me zoom out and zoom in something else. The red curve is the current that is passing through the inductor, okay? And as you can see, it's almost like a kind of a triangular waveform, okay? So from now on, we pretty much assume the current of the inductor is triangular in power electronics, and later we have to kind of design the inductor in a way that it looks like a triangular waveform. our system is a second order system. We have an L and we have a C. So there should be some sort of a resonance going on. But because our switching period is much smaller than those resonating periods, we don't really see the entire resonance. We only see a very small portion of that resonance. And that very small portion looks almost like a straight line. So this is kind of indicating that from here to here, that my switch is turned on, the inductor current kind of ramps up. And then from here to here, when the switch is turned off, the inductor current ramps down. So inductor current ramps up means we are energizing the inductor. The inductor current ramps down, we are de-energizing the inductor and delivering the power to the load. So it's like a sequence of energizing and de-energizing of the inductor. Okay, let's zoom out again and look at the output voltage. This blue one over here is the output voltage. So let me just zoom in. You can see it's almost DC. There's a little bit of a ripple in it. But if you look, it's around 12 volts. So remember, duty cycle was 60%, input voltage was 20 volts, and there is no wonder the output voltage is 12, because as it turns out, the output voltage in this converter is the input voltage multiplied by the duty cycle. Input voltage was 20, duty cycle was 0.6, or we wanted 60% of the 20 volts, and that gives us 12 volts. So again, as you can see, the output voltage is almost DC with a little bit of ripple. So if you zoom in, you can actually see this ripple. And you can, for instance, in this particular case, measure the peak-to-peak ripple of the voltage. So you can see it goes as high as 8 millivolts above 12 volts and a little bit, I would say 7 millivolts below 12 volts. So if you look at the peak-to-peak ripple in the output voltage, compared to 12 volts, almost nothing. In other words, if I zoom out, I almost see a DC voltage over here. All right? So again, when we are analyzing the converter, I'm going to assume that the output voltage is almost DC. And you can see it's almost DC over here. And then later on, we have to find an equation based on which we can design the capacitor to give us a constant output, relatively constant output voltage. Now let's verify this again. So let's say now, instead of having 12 volts on the output, I only need 5 volts on the output. Let's do that. So 5 is 25% of 20, so I have to adjust my duty cycle to 0.25, okay? And then you run it again. And now you can see this blue is my output voltage. It is at 5. You can see it's exactly at 5, but the same phenomena holds. Your inductor current ramps up and down, and this is the command that I am applying now. For 20% of the time, 25% of the time, my switch is on, and for 75% of the time, my switch is off. Very, very simple. Okay. So what we are going to do now is, any questions, by the way? What we are going to do now is kind of analytically, prove that these equations hold. For instance, output voltage over the input voltage is the duty cycle. Find a waveform for the inductor current, and things like that. So I'm going to post this on Blackboard. I think Plex is installed on all of the computers, at least in the EE department, all of the lab computers, so you can actually use them. And let me know if you have a problem. There are 2 versions or 2 different ways of Plex. One of them is a standalone kind of a thing that I don't have it here, and one of them is like a MATLAB-based Plex. What I'm using here is the MATLAB-based, and my version of MATLAB and my version of Plex is the most recent one. And you may not be able to open the file. If that's the case, let me know, and I will send you something that you really need, basically. All right, so going back to OneNote. All right. So as you can see, you can identify 2 modes of operation here. One mode is switch is on. One mode is switch is off. And remember, whenever we have a diode in the system, we have to figure out, okay, what happens to the diode in each mode. So looking at mode 1, okay. Okay, switch is turned on, and it's an ideal switch. It's assumed to be an ideal switch, so when it is on, that means it's like a short circuit. And how long does this last? This is lasting from the beginning of the period all the way through duty cycle times period. Okay, so this is how long this mode lasts. Okay, which is basically this over here. And okay, so let's look at the schematic. All right, this is the input voltage. It's a DC source. The switch is turned on, so I just replace it with a short circuit. I don't know what's happening to the diode, so I just draw it as a diode, and then the rest of the system. All right, something like this. So if you look, you're going to realize that from anode to cathode of the diode, we are applying a negative voltage, meaning that the diode is off. So if you look at the voltage drop across the diode, it is negative Vn. And assuming that my input voltage is positive, which is the case, then the voltage that appears across the terminals of the diode is negative. So the diode is reverse biased, the diode is off. Okay, so a diode that is off looks more like an open circuit technically, so I can actually replace it with an open circuit. All right, something like this. Okay, so diode is not in the picture at all. So, and I am assuming that I'm looking at the system under steady state conditions, meaning that the output voltage has already built up to a particular value. It's almost DC. So let's look at the voltage that appears across the terminals of this inductor. Okay. I mean, if you apply KVL around the loop, this is the loop we're talking about. So VL is Vn minus V out. Very, very simple. All right. Okay. Why do we care about VL? Because if you're analyzing the system under steady state conditions, that means on average, the voltage of the inductor should be 0, and that gives us a basically voltage transfer ratio. So this was mode 1. Let's talk about mode 2 now. Or maybe here I should also talk about what happens to the current of the inductor. Maybe it's a good time to do that. So I have an inductor and there is some positive voltage applied, positive and constant voltage, because Vin is already constant, V out is almost constant. So almost VL is constant and positive. If you have an inductor and such a voltage appears across the terminals of the inductor, the current of the inductor is going to rise. Okay, so it starts from some minimum value. We label it to be I min. And rises to a maximum value of I max at the end of this period. And if you are interested in the mathematical description, you can argue that, okay, IL is the initial value of the inductor current. We don't know how much it is, but it's there, plus the slope The slope is the voltage across the inductor over L times time. And obviously time is the only variable over here. Okay? And this one is, in my notes, is labeled to be equation number 1. All right? The other thing is, I am assuming that this is positive. And later on, we have to come back and double check and make sure it is really positive. So far, I'm assuming that my input voltage is larger than the output voltage, but I have to verify that towards the end. In the simulation we saw, the input was 20, the output was 12. But I have to verify that. Because this input voltage is positive, this slope is positive. Therefore, the inductor current rises. Okay? Now, let's look at the... I have a bunch of equations that I don't really need it now, but I have to write them because later we are going to use them. One of them is I max. I max, the maximum value of the inductor current. That means the final value of the inductor current. All I have to do is just evaluate IL at time instance of dt, and that gives us I min plus Vn minus V out over L times D times T. Okay, so this is an expression for I max, and this is labeled to be equation number 2 in my notes. And the other one that comes in handy is how much did the inductor current rise? We call it delta IL, okay? The changes in the value of the inductor current from the beginning of the period all the way to the end of this mode. So delta IL is basically I max minus I min. And from equation number 2, you can easily say this is Vn minus V out over L times the duty cycle times the switching period. All right. And we are going to need this later. All right. So this was mode number 1. Let's talk about mode number 2, and that is when we open up the switch. Okay? Mode number 2, switch is turned off. Again, we have to make a decision about the diode. What happens to the diode? Okay. So if you look at this schematic, the inductor has some non-zero current. And in the first mode, this current is passing through mode number 1, switch. It's passing through the switch. But as soon as we open up the switch, like this, there's no way that it's going to conduct that current anymore. So this current of the inductor, which has to be continuous, has to go through somewhere, and what it does is it chooses this way. Okay, so it kind of forces the diode to turn on. So as soon as you open up the switch, the inductor, which has non-zero current, forces the diode to turn on. Okay, let me clean this a little bit. Okay. So switch is turned off. IL is not 0, it's positive. It's actually at its maximum value of I max. Therefore, or let me write it in a better way, IL at the beginning of this mode is positive, and therefore L forces D, inductor forces the diode to turn on. Okay. And by the way, the duration of this mode is the second segment of the period. All right? So if you look at your schematic now, it looks like that. So basically, D is on. We have a switch that has been turned off, so it's like an open circuit. we have a diode that has been turned on by force of this inductor, and then the rest of the system. All right, so this is your new, basically, system with diode on, switch off, mode number 2. And again, if you look at VL now, the voltage across the terminals of the inductor, and obviously to find VL, we have to write KVL in this loop, and that gives us VL is negative V out. I'm assuming that the polarity of the output voltage is in this way, in this polarity. All right. There are a bunch of other equations that we are going to talk about next time because we're going to get to the quiz. And so all of these equations, everything that I wrote over here, they are already here in my notes. So if you want to get a head start, you can actually look at these equations. So like mode number 1, mode number 2, so basically we covered all the way up to VL is the negative of V out, okay, in this mode. So we are going to start the quiz now. Just write it over here, quiz number 2. And so we have about 10 minutes. It's a very simple, straightforward quiz. If you have an equation sheet, use it, but I don't think you really need one. And but your notes and your book should be closed. And like the previous quiz, when you're done, please don't get up and leave the room. Just sit, and once everybody's done, I'm going to collect them all together. All right, so you guys just go zigzag down that road. Same here, zigzag, go to the back rows. And here. Here, here's for you too.